Institute there, and then went on for postdocs at CISA and Karlsruhe, and then Taiwan, the National Center for Theoretical Sciences. And since 2018, he's a faculty member at Taiwan National Tsing Hua University. And he's an expert, or very well known for his work on flavor symmetries and work on grand unified theories and to predict the flavor structure. But today he will be talking about a different topic. He will be talking about cosmic relic scattering at gravitational wave detectors. So Martin, please.
Okay. Yeah. Thanks. First of all, thank a lot for the invitation. I would be more happy to come to Sydney than this one, but of course, yeah, these days it's very difficult. Still, I'm happy to share my work with you, and as Michael already said, so this is something I started working on only recently, and I might say some wrong things because I'm not really an expert, so please forgive me. But I still hope it will be interesting for most of you. Yeah. So this talk is mostly based on the 3 papers. The first one was Valerie Domke, then with Cheng Ting and Rainer Primolando, and then the third one with Junhao Li and Cristiano Grovo. Yeah, I will of course label this properly. So hang on, okay. So this is sort of my talk. I will start with some introduction. Then I will first briefly talk about cosmic background, how things started off for me with this different direction. And then we'll talk about dark matter, yeah, and then I will summarize and conclude. So let's start with introduction. So cosmic relics, what are cosmic relics? So cosmic relics, very roughly speaking, they're produced in the early universe and they're still around today. And there are 3 famous examples, I would say. There's first of all the cosmic microwave background. This one is super famous and everyone has seen the picture, but this is not the focus here. Yeah, I will not talk about this. Then there's cosmic neutrino background, which is basically the same thing. I will say a few things later on, but there's no direct observation yet. Yeah? So we didn't see the neutrinos from the cosmic neutrino background today. And then there's also dark matter, which we believe exists. We have only seen it gravitationally. So only seen there is some matter, which has some gravitational interactions, but we also don't really know what this is. So there is no direct or other indirect observation beyond gravitation, which we have for dark matter. Yeah? So these are the 3 examples, I think, which are the most famous ones. So what is the cosmic neutrino background? So you know how the cosmic microwave background is produced. So the early universe was very dense and very hot. And at some point, the photons decoupled from the thermal plasma. The same thing happened with the neutrinos. So they also decoupled from the thermal plasma, but they actually decoupled much earlier than the photons. So the photons decoupled roughly 380,000 years after the Big Bang, while neutrinos decoupled roughly 1 second after the Big Bang. So this is much earlier. And that is actually quite interesting because if you could see them, that allows us to test much earlier universe than with the CMB. So then we can also do this exercise and try to predict how many we would see today. And if you assume standard model neutrinos and standard cosmology, nowadays you would expect roughly 300 neutrinos per cubic centimeter, which should still be around today. So the temperature we can also test should be roughly about 1.9 Kelvin. That means the average kinetic energy is of the order of 0.5 milli-electron volt. And this is small. This is a small number. Yeah, actually it's a similar number to the CMB, but there's a problem with this, yeah? So the velocity today, depending on their mass scale, you know, one neutrino can be massless, but 2 of them definitely have mass, but that has some impact for their velocity, depending how heavy they are. It can be somewhere between 10 to the power -3 of the speed of light or up to the speed of light if they are massless, of course. Yeah? The problem with these guys, why we didn't see them today, is not the abundance. The real problem is the cross-section. If you do this exercise and say you take a neutrino with 0.5 milli-electron volt energy and shoot it onto a neutron, and calculate the cross-section, you end up with a number which is 10 to the power of -27 picobarn, or 10 to the power of -63 square centimeter. Just to give you a scale, the LHC nowadays is testing roughly picobarn cross-sections. Yeah, so we are very far away from these numbers. This is the real problem, the cross-section, and also the small energy actually. What could save us somewhat is if you compare neutrino fluxes. This is quite interesting and most people don't know about this, I think. If you compare the neutrino flux on Earth for different sources, actually what you can see is that the cosmological neutrinos, this cosmic neutrino background, has a much larger flux than any other source which you have actually seen, like solar neutrinos, reactor neutrinos, atmospheric neutrinos, all of them we have seen. But the CMB we don't have seen. Yeah? And also note that this is a log scale. Yeah? This is a log scale. So you might wonder if this flux can compensate the small cross section somewhat. And yeah, you will see. So this is got new background. What about dark matter? Dark matter is probably the biggest topic these days in particle physics and astroparticle physics. There's plenty of evidence for its existence. So for instance, there are these rotation curves. So you measure the velocity of stars and galaxies, and then you just calculate the velocity according to gravitational law. And then you see that somehow there seems to be mass missing. Yeah, and this could be, for instance, dark matter. There's this Chandra picture of the Relic cluster. So these pink regions here, this is visible matter, while actually this blue blobs here, this is actually the gravitational matter. Yeah, and you can explain this by saying this blue blobs, this is dark matter. So there are two galaxies which crossed each other, and then the visible matter, they slowed down and they cluster here, while the dark matter, they just move through each other without feeling each other. So they are faster than the visible matter. Yeah. And yeah, the CMB also gives you some information about matter content of the universe. And then you also realize that there's more matter than we actually see. Yeah. So there are more evidences. Some of this you can also debate, but many things point towards some kind of dark matter, which we see mostly in terms of gravitational interactions. So we believe it exists, but we would also like to know what this is. So now let me try to make the same slide as before for the CMB. So cold dark matter, what do we know? We don't know when it was produced after the Big Bang. We have some information about the local energy density. There are some estimates, which are somewhere of the order of our data also, which suggests it's at the order of 0.3 to 0.4 GeV per cubic centimeter. We do not know its mass. Yeah, so this dark matter particles could be super light, 10 to the minus 22 eV per square per c squared, or there can be as heavy as 10 to the power 5 solar masses. Yeah, everything in between is in principle possible. So we have some idea about the local peak velocity because dark matter I should class in our galaxy for the rotation curve stuff. So then it should be virialized. So we have some rough idea about the local velocity. But we have no idea about its cross section to ordinary matter. Yeah, there's some bounds for different mass regions, but we don't know. Yeah. So cold dark matter, you see, there are many question marks compared to the cosmic neutrino background, which is good and bad. Yeah, you will see what I mean by this. So this is well, I mean, when I started particle physics, people, when they talk about dark matter, it was mostly WIMPs. And WIMPs at this point was by many people identified with neutralinos. Yeah, so SUSY particles should be 100 GeV and have a V cross section. It should have interact basically with the Z boson. And then you get the WIMP miracle and everything works out perfectly. So people went to look for this because it was so perfectly motivated. Unfortunately, so far, there is no evidence for 100 GeV dark matter particle. Yeah, these are more or less the current bounds. So you see this is the cross section with ordinary matter, and here you see the WIMP mass. But these experiments, they're optimized more or less for the GeV mass region. This is where they're most sensitive. You see this is somewhere here at 20 GeV or so, and 100 GeV is also very good. But at lower dark matter masses, they lose sensitivity because they have some energy threshold, which cannot be crossed by light dark matter. And also for heavy dark matter masses, you have a problem because the number density goes down for dark matter particles, and then you also lose sensitivity because, yeah, there are just not enough particles there to interact with the detector. So because of this, negative searches also at LHC and stuff, where they didn't find any new particles at the TV scale, which doesn't mean they don't exist, but I mean, they didn't find them. So many people are nowadays thinking beyond this 100 GeV mass scale. Yeah. And I also want to think about this in my talk, and I want to go towards lighter dark matter masses. What can we do there? Yeah. Because this is also very motivated if you compare to neutrinos, because in fact, neutrinos make a tiny fraction of dark matter. We know that they are there, but they cannot form all the dark matter. Yeah. So but there's a similarity in some sense. So the third motivation is coming from gravitational wave detectors. So here, this is a picture from LIGO Livingston. You see, this is an interferometer. I guess you're all familiar with interferometer. So you see here the two arms of the interferometer. And these are the LIGO test masses. So you see, this is basically the mirror with some compensator mass. I think this is the mirror actually. And I don't know if you can see this over this transmission, but there are also some very thin wires. So you see this is basically a pendulum, yeah? So these mirrors are pendular. That would be very important for the rest of the talk, yeah? And why is this so important? Because these things are extremely sensitive, yeah? They went through decade-long R&D efforts. They have very impressive sensitivities. They can measure very tiny displacements. They got Nobel Prize in 2017 for the discovery of gravitational waves. Absolutely deserved. It's a great discovery. What I want to ask in my talk is also, can we actually use this technology also for other things than looking for gravitational waves? Yeah? Which would of course be interesting if you can use this for other things as well. So these are the three things which I will talk about in my talk. So let's start with cosmic neutrino background. This is how things started off for me. So in 2017, the paper came out. Actually, I started talking about this with Valerie in Karlsruhe. So this is the idea. Yeah, you take a pendulum, like they use in LIGO basically. And then because the neutrinos, because the Earth is moving in this bars of neutrinos, which are everywhere, we have a relative velocity towards it, there should be a neutrino wind. And this neutrino should interact with your test mass, your pendulum test mass, your mirror. So they should push it around a bit. And in principle, you can try to look for this kind of effect. Yeah. And if you do this exercise and you do make some naive estimate on what kind of accelerations you can test, because this acceleration depend on how good can you measure this, the displacement of the mirror, how precisely can you measure this. And if you make some very rough estimate, which experimentalists won't like, we'll come back to this later, you can maybe test accelerations down to the order of 10 to the minus 16 centimeters per second squared, which is a very tiny acceleration. Yeah. In the future, they talk about iGen telescope, which is a generation even after KAGRA. They might become better by a factor of 30 or so. Yeah, to give you some idea on how well things will improve in the future. So the question is now, does the CMB wind create an acceleration or force on the target which is larger than this threshold? Yeah. So to do this, we do some scattering. So we just assume that the neutrinos scatter from our target mass. And we know this basically because of this weak interaction. So this is a well-known process, also not at these energies. So this goes into the formula. So the acceleration is equal to the Neutrino flux. Then the number of nuclei in 1 gram test material, basically the number of scattered objects. Then you have the neutrino nucleus cross-section. And I already said that this is a small number. So this is a problem. The coherence factor will enter. I will come back to this on the next slide. And you also get average momentum transfer. Yeah. So basically the question is how much momentum that transfer on your target. Yeah. And for this average momentum transfer, you should know that neutrinos, they can come in 3 kinematics. So when they are massless or very light, they're relativistic. When they are heavy, so they're non-relativistic, but then they can be still fast enough not to class in our galaxy. Or they can be non-relativistic, so they're heavy and they class in our galaxy. And this will tell you something about their velocity distribution. This will tell you something about their momentum, and this will tell you something about the average momentum transfer. So you get 3 different numbers for these 3 scenarios. And yeah, then you also have to know the cross-section. This one I already mentioned before, is very small. It's 10 to the minus 27 picobarn. The good thing is, which might help you a lot, is the coherence factor. So what is coherence factor? The point is that these neutrinos, they have small kinetic energies, but that means they have long wavelengths. And they have wavelengths at the order of 0.1 centimeter. That means when they go through your target, they will not just scatter from one single atom. They will scatter from all the atoms within this blob of 0.1 centimeter, because this is what they can resolve. That means they get a huge coherence factor, yeah? Which people actually saw now at 1 nucleus. We want to do this at several nuclei. And in fact, this is at the order of 10 to the power of 20 nuclei. Yeah, because yeah, a volume of 0.1 centimeter cube contains really a lot of atoms, yeah, roughly 10 to 20 atoms. So we get a large coherence factor, which means that actually the cross-section is somewhat larger, actually many orders of magnitude larger than you naively expect, because you don't scatter from a single neutron. So then you just plug in some numbers and you end up for the acceleration, depending on the kinematics. The most optimistic case is for the non-relativistic clustered neutrinos. You end up with a number which is at the order of 10 to the minus 27 centimeters per second squared. So you see this is actually quite many orders of magnitude below what you can do with LIGO in principle. So this idea doesn't really work out, unfortunately. But then what can you do? Let's have a look at some other wins. I think this is instructive. So first of all, you can ask yourself, could you see solar neutrinos in this way? Of course, we have seen solar neutrinos in other ways, but we can have a look. Why not? Yeah. So, sorry. Sorry, there was a question.
Let's continue. I think it was the interference.
Okay. So solar neutrinos we have seen already, but we can still ask, can we see them in this way? And the answer is actually we can also not see them, which might be confusing because they have much more energy. That means they transmit much more momentum. They also have a much larger cross-section. That means it's much more likely that they will interact. But because they have so much energy, they do not have the coherence factor. Yeah? And that makes them also not suited for this kind of experiment. So actually they're only a factor of 10 better than the CMB neutrinos. Then you can talk about WIMP dark matter, because also we are moving with respect to the WIMP bars. So we can try to do this exercise. And if we take ordinary WIMP dark matter with masses above 1 GeV, we also end up with very small accelerations, simply because there's a very stringent constraint on the cross-section. Because the cross-section is small, they give a very small force. But things change if you go to light dark matter, because for light dark matter, first of all, you can again get a coherence factor. That means your cross-section can be enlarged. And second of all, the constraints on the cross-section are much smaller. So you can get larger cross-sections. So there is some room for potential discovery. Yeah, and this is what I want to explore now in a bit more detail. So let's talk about dark matter. Yeah, and yeah.
Sorry, I have a question. Sorry,
Yes.
I have a question. What makes cosmic neutrino flow? Or
Cosmic neutrino.
yeah. Or indeed, do we move, and as a result, relatively, we feel that the cosmic neutrino flows? Sorry, my English is not good, so can you understand my question?
I think your
namely,
first question.
what's the source which makes cosmic neutrino flow?
So the cosmic neutrino flow, I think the one you are talking about is the one which people talk about in dark matter dark detection experiments, right?
Sorry, could you say again?
So you are talking about what people call the neutrino floor in dark detection experiments for dark matter, right?
Yeah.
So this is, I think this is a bad name, because this is actually astrophysical neutrinos, or neutrinos which are produced in the atmosphere. They are produced in the solar system or from the diffuse supernova background. So they're different sources, but they are not, this is not the cosmic neutrinos which were produced during BBN. So they were not produced in the very early universe. They are produced much later, and they have much higher energies compared to what I'm talking about. So this is they also call it cosmic, but I think that they should not do this.
Yeah. Currently, you looks to suppose that the cosmic neutrino is flowing, right?
Is
And
what?
flow means. Please, could you go back to a few slides?
Just say stop, yeah?
More, please, more back. Yeah. At this page.
At this page, yeah.
You looks to suppose that the cosmic neutrino is flowing, and as a result, pendulum oscillates.
I think
Yes.
the question is about the flow. You know, the flow of cosmic neutrinos. What causes that?
Yeah. This is because the Earth is moving with respect to the neutrino bars. So the most naive assumption you can do is you say the cosmic neutrino background has the same distribution as cosmic microwave background. And we know that the Earth is moving with respect to the cosmic microwave background with a certain velocity. And this effect we should also see with the cosmic neutrino background. And then, of course, the Earth is rotating, and the Earth is rotating around the Sun. That will mean there's the velocity is not constant. There will be some daily and annual modulation on top of this. Yeah, and then
I see.
Yeah. Yeah. Okay, so let's move on with dark matter. So let's start with dark Brownian motion. So what is the idea behind this? So before actually what we did, we basically averaged over all the scatterings. And now we don't want to do this anymore. Let's talk about individual scatterings. So we have our target mass, and this target mass is in the mass of dark matter because dark matter should be all around of us. And then if we assume that the dark matter scatters from the target, that will induce something very similar to Brownian motion. Yeah, so they will get a kick from here, get a kick from there, and then your target mass starts to move. Yeah. Also, we are moving in this path of dark matter scatterings. So the direction changes somewhat. We always get scatterings from all directions, but there will be preferred direction or a direction with larger recombinanta depending on where you are in the time of the year or the day. Yeah, I will show you some figures later. This is the idea now. Now let's try to look for this dark matter-induced Brownian motion of a target mass. Yeah, with individual scatterings of dark matter with the target mass. So, so this is I took this slide from my student Tim Cheng. She's now went to Heidelberg to do a PhD. It's again a very similar setup we had in mind. So we do an interferometer experiment or some other way to measure our target mass, and we have something like a movable mirror or object. Yeah, and this one will test the scatterings with the dark matter, and then if you measure the position of this target mass, we're looking basically for some jump in the position or the momentum. Yeah, so that means it got a kick. So this is what we want to look for: some kicks in the motion of this target. So let me just show you the figures for the time dependence. So if this is the figure, so this is the sun. This is the Earth rotating around the sun, and the dark matter wind, people figured this out. Dark matter comes preferably from this direction. Yeah, so it should be the strongest on June 1st if the Earth is moving against the dark matter wind, and should be weakest in December 1st when the Earth is moving along the dark matter wind. Yeah. If you would make an experiment in Hsinchu, let's say, because yeah, that was where we were at that time, you can also plot the lap velocity with respect to dark matter wind in north-south direction and in east-west direction. Yeah, of course, this is a 3D effect. Yeah, depending on which direction you're pointing it. And then what we want to measure is, or what we suggest to measure is an asymmetry factor. It means we count basically. So we look at this target, and we count how many hits it gets and in which direction the momentum points. Does it point into positive direction or does it point to negative direction? Yeah? And then we just take the difference and normalize it with the sum of the events. And this is typical distribution, which we simulated for the momentum. I forgot at which time it was, but this is basically how it looks like. Yeah, you would take many events. You would get this kind of asymmetric distribution simply because the wind is coming from a preferred direction. Yeah, and you also see that here this one stretches out to larger recombinanta because it has higher velocities. And then you can plot the daily modulation of A, this asymmetry parameter. Again, this is for north-south and east-west direction. If you paid careful attention, you would see that the sign flipped. This is because we defined it in this way, depending on how you define the sign of this. And the error bars would be if you assume a 10-minute data taking, a dark matter cross-section of the order of 10 to minus 31 square centimeter, which is not excluded at this point, and dark matter mass of 10 MeV. If we assume a target mass, no, actually that doesn't matter. Yeah, at this point. Yeah, so this is, of course, this is pure theory. Yeah, here we didn't do any backgrounds. So what about backgrounds? which is probably the critical issue. Yeah, I mean, this in theory, we can do everything perfect and then no problem. Yeah, but of course, experiment is not so nice to us. So there are many backgrounds you can think about. Yeah, there could be seismic noise, nearby traffic, radioactivity, people being in your lab, all kinds of stuff going on, which would all make this experiment very difficult. Yeah, because this is obviously a tiny effect. Yeah. So let me discuss two examples. One should be neutrinos, and the other one would be hits from residual gas, because yeah, there will be still some gas in your chamber where the target mass is, so that should always give you some Brownian motion from the gas which is still there. So the background from neutrinos, this will always be there because we cannot shoot neutrinos. They always go through all materials. But if you go to this setup, because we propose small target masses, yeah. So the flux of neutrinos is large. I took now solar neutrinos, yeah, and the cross section is small. That's the point. And if we take a target mass of 10 to the minus 3 grams of carbon, which is our benchmark scenario, then we expect 10 to the minus 14 neutrino events per second. So this one we can forget, because basically never a neutrino will hit our target, which is not a surprise because we see neutrinos need large detectors. Yeah? And we want to have small detectors because we want to have a larger recall energy. So what about residual gas? So actually, these gravitational wave detectors have ultra high vacuum in the chambers. So let's assume we also have this. And then we can estimate the hit rate from residual gas. And this is simply this formula. You take the number density of the residual gas, you take a cross section, which is basically the area of your target. You take a velocity and then the velocity distribution, which is the Maxwell-Boltzmann distribution, let's say. And then you end up with a number which is at the order of 8.3 times 10 to the power of 9 events per second. So this ultra high vacuum still has a lot of gas atoms inside. At least you could see a lot of them. So this is the typical numbers. This is for 20 Kelvin if you assume KAGRA-like a setup, and this is the pressure in the chamber, and this is basically for a millimeter squared setup. So we take a small target. So let's compare dark matter rate. If you compare dark matter rate, if you take similar numbers, 10 to the minus 3 carbon, cross section 10 to the minus 31 square centimeter, dark matter density 0.3 GeV, and so on and so forth, we end up with an event rate which is at the order of 0.4 per second, which is optimistic but not excluded. Yeah. So now you see there's a problem in principle. The question is then, can we cut on the background? And the answer is yes. Otherwise, I would not talk about this. Yeah. So how can we cut on the background? So let's do this. So first of all, we want to assume there's no airflow in our chamber, which makes the calculation easier. And then the width of the momentum is this one. So this is basically, if you take the distribution of the momenta, this is 0 because there's no airflow, but there's of course some uncertainty, yeah, because you still get hits from all directions, and this will only be on average 0. So you get a wish, and you do some statistical physics, and then you end up with this number. So it's roughly 2.5 times 10 to the minus 24 kilogram meter second. And this is the point now. If you take LIGO resolution as in some naive estimate for what we can resolve, LIGO can resolve something like maybe 10 to the minus 23 kilogram per meter second. Yeah, and you see that this number is larger than what you can see. Now, this is larger than this uncertainty, and this makes sense because LIGO actually, they don't care about the noise from residual gas atoms. Yeah, and this is why they don't care about this, because they cannot see this. Yeah? It's just not there. If you do this, actually, you see that after you apply this cut, you only get an event rate of the order of 5 times 10 to the minus 6 hertz. Yeah. So, and then you see that you can forget about this. Yeah. The point is, what you should do also is you need a very good time resolution. Yeah. So you need a lot of time bench to resolve this. So then if we do this, we can show some curve. This is on the vertical axis is the cross section. On the horizontal axis, you see this is the dark matter mass. If we again assume LIGO-like setup, we include these two backgrounds I mentioned. Actually, the neutrino background, you can forget about this. So an idealist experiment, if you would have no background whatsoever, in principle, you can exclude this line here, yeah, the black line. Yeah, but if you include the background from the residual gas, First of all, you cannot resolve small recombinant matter. That gives a cutoff. So if your dark matter becomes too light, you don't get large enough recombinant matter anymore. And yeah, then you also lose because you get noise. Yeah, and this is what you get. Yeah. But still, this is remarkable. Yeah, this is only for 10 minutes of data taking. And yeah, of course, there are some generous interpretation of what you can do, yeah, because it's not clear that you can scale down LIGO to this kind of setup. But let me show you some figure which is actually reality. So this came out very recently. So they used an optically levitated mass, and the target mass is 1 nanogram, and they measure the position of this target mass with very high precision as well. Actually, with much less precision than LIGO can do. But this is a small scale experiment. It's like 10 people in the collaboration. It's in Yale, just people from Yale. It's a new technology, so it's really unfair to compare to LIGO. And actually right now I talked to them and they said their biggest uncertainty right now is actually coming from the optics. So there's room for improvement. They have very low temperatures and several days of exposure, and then they can also constrain dark matter masses. But you see, they're talking here about, yeah, GeV dark matter masses. Yeah, so very heavy dark matter masses compared to what I was mentioning before. But this is, well, right now the biggest noise is optics, yeah, and then in the future I'm not sure which one will be the dominating source. Yeah, so it might be that we can actually not go down to mega electron volt dark matter masses, but that's future research. I don't know yet. So this was actually a particle physics approach, yeah. And I had the feeling when I talk to particle physicists, everyone understands what's going on. If I talk to gravitational wave people, they're always like very much, what are you doing? Why are you doing this? It all doesn't make sense. So now I try to present things in a language which I think gravitational wave people can understand better, yeah. So what do we do? So again, we take a harmonic oscillator. So KAGRA, we will use KAGRA as an example. So KAGRA actually presents numbers using a complex spring constant. Yeah, so you have the mass, then you have a spring constant, and then you have a complex factor here. And this one actually leads to some damping. Yeah, so you have a damped harmonic oscillator by this phi here. This is all nice, but actually, if you think about forces and stuff, it's more intuitive to talk about the real equation. And the real equation would look like this. So you can get the mass, then you get here some the oscillation frequency, and you also get some damping factor. Yeah. I will later say how we match this quantities omega r and psi to these quantities here. Yeah, this is actually gave us quite some headache for some time. And then the experimental output, the total displacement which you can see in your experiment. Let's say it has 3 components. First, there's a dark matter signal. There's something which I call quantum noise, and there's something which I call suspension thermal noise. So let's talk about these 3 components, yeah, one after each other. Let's start with the noise. So the thermal noise is actually, it's just thermal noise, yeah. So if anything has a temperature, it means it will fluctuate somehow, yeah. And there's a fluctuation dissipation theorem, which tells you how does the power spectral density of the thermal noise look like. Yeah, so basically, it tells you about the thermal fluctuations. And the relation is this one: the thermal fluctuations are proportional to the temperature, of course, so the thermal energy. And then this is the real part of the impedance of your system. Yeah, so it's basically how your system responds to external forces. Yeah, I don't want to talk about this. This is not also really our work. But if you go through this exercise, it's actually not so difficult. You will find that this thermal noise is given by this formula, so it's proportional to kBt. Then you have here the omega c is the frequency of the complex case, phi is the damping of the complex case, the mass, there's some frequency dependence here, and L is actually the arm length of the oscillator. There's also something which is called standard quantum limit. And this is basically, you know, there's quantum mechanics, you have some, you always have an uncertainty relation, yeah, between position and momentum. And that means you cannot measure both at the same time with infinite precision. That means if you try to measure the position of a pendulum, you will always get some uncertainty, some intrinsic uncertainty. And this is the standard quantum limit. Yeah? And people figured out how to do this. And the formula in frequency domain is this one. Yeah. So this is just a formula. So the strain amplitude, what people observe is then just this quantity here. Yeah. So this is the noise components we look at. Yeah.
Sorry, what's M?
M is the mass of your oscillator. So
I
for
see.
KAGRA, this is about 20 kilograms.
I see.
So what about the dark matter signal? For the real case, this is actually easy to model. So this is the harmonic oscillator, the delta harmonic oscillator. And then what we can just do is we assume some delta force, so pulse force, yeah? So if there's a short range interaction, you would say the dark matter comes in, it scatters from your target, basically instantaneously, and then it keeps on moving, and it transmits a recoil momentum, which we call QR. So QR is recoil momentum imposed by dark matter on the target. That has a standard solution. So this displacement here is then theta function because we make the hit at t equals 0. Let's assume there's no excitation before. And then you just get here QR m omega L is exponential. You see this is damping here. And this is the oscillation part, yeah? So, and then because we want to do everything in frequency domain, this is what gravitational wave people are doing. They do everything in frequency domain. It takes a Fourier transform and takes the modulus squared. Yeah, so this quantity will appear again. This is important. So now the point is we have to match the coefficients, yeah? Because the question is this omega r and the psi here, how do they relate to omega c and phi? Because these are the numbers we can get from KAGRA. And what we want to do is we just assume that the oscillation frequencies for both cases, the complex and the real case are the same. And we also assume that the amplitude damping, that means the exponential decay of the amplitude, is the same in both cases. Yeah, and then we can just compare the equations and solve for it. Then we find that omega r is roughly the same as omega c plus this phi squared correction. And psi is equal to phi over 2 plus this phi squared correction. And phi, you have to know for KAGRA, these are high quality oscillators. So they have phi of the order of 10 to minus 6, 10 to minus 7. So we see they're basically the same. There's a very small difference. Yeah? So the dark matter signal then, if you express this in terms of omega c and phi, is this formula. So it simplifies. And the strain amplitude, which people usually show then, is simply 2 omega over pi square root times this x tilde. Yeah, the modulus of this x tilde. So this is how it looks then if you do this realistically. So on the vertical axis is the strain amplitude in square root 1 over hertz. This is an unit they use. And on the horizontal axis here, we have the frequency in hertz. And here we used some numbers which are inspired by KAGRA to get the frequency and the damping, so the phi and the mass and the temperature also. So all the parameters are inspired by KAGRA. And we assume that the recoil momentum, which we use, is 1 GeV times 220 kilometer per second, which is a rough estimate. Yeah. So standard quantum limit, you see it's just this blue line, it's just falling. And what you see here, this is important, is that the dark matter signal follows basically the thermal suspension noise. Yeah, this is because both of them show this resonance structure. And that makes sense, yeah? But you can also see that the dark matter signal usually loses compared to thermal suspension noise. Of course, we could simply postulate that we make the mirror super cold. But you see there's quite some gap, yeah? There's linear in temperature, yeah? This is a bit difficult. The other thing we can do is, wait, let me show you the next slide. So how can you do this a bit more quantified? So usually people talk about signal to noise ratio, yeah? And the optimal signal to noise ratio is given by this formula. Rho squared equals, then takes the integral over the frequency of the signal divided by the noise. Yeah, and here we use, actually you see in this figure that if you are here in this range, frequency range, you can forget about the quantum noise, the thermal noise is dominating. And if you do this, you find that the signal to noise ratio is given by this formula, very simple exercise. Actually, this takes a full width half maximum. And then you see that this is the ratio of the recoil energy, QR squared over 2m, divided by the thermal energy, KBT, of your system. And this is super tiny. So if you want to make this larger, what you need is light targets. not 20 kilograms, but much lighter, and cold targets. So not 20 Kelvin, but ideally close to 0. Yeah, 100 microkelvin or so, super cold. Yeah, and very light ideally. Then you can get a signal to noise ratio which is sizable in principle. So let's have a look at KAGRA. Yeah. So this was a toy example, very easy. Let's have a look at something more realistic, yeah, just to see how things play out. So KAGRA is a new gravitational wave detector in Japan, the next generation of gravitational wave detectors. The advantage why we take KAGRA and not LIGO, for instance, is KAGRA is cryogenic. So the temperature is about 20 Kelvin. While in LIGO, they don't have any cryogenic system. So their temperatures are, I think, not really room temperature, but not so far, something like 200 Kelvin or so much hotter. So the mirror is a pendulum on springs on a pendulum. Yeah, this is a complicated sentence, but here you see the picture. Yeah, so here, this is the mirror, this is the test mass. Then it's hanged here on this you don't see here, but there are some springs, some blade springs. And then you have some intermediate mass, yeah, which is again a pendulum. So you have actually 3 coupled damped harmonic oscillators. So your equation of motion become more complicated. Yeah? So your equation of motion take actually a matrix form. So there's a mass matrix that contains the 3 masses of the intermediate mass, the blade springs, and the target mass. And here this K matrix contains this complex spring constants. Yeah, but this is all public, so we could just use the published data from this document here. Yeah, and then of course we have to again impose some external force. And then there's also one thing which is important. KAGRA, you always believe it's one-dimensional because it's interferometer. You also can believe you can only test one direction. But this is not quite true because the arms are long enough and they're so sensitive enough that they can also see, if you want, the pendula are not completely straight. They're a bit tilted because of the bending of the Earth. Yeah? And they can see this. That's why they can also see a little bit of the vertical mode. Yeah? If you would check one of the mirrors in the vertical directions, I could still see this. Yeah? That also has some impact on the relative position of the 2 mirrors. So actually you get 2 sets of equations. Yeah? So if you do this for the noise, actually you get this fantastic picture. This is very messy. So let me try to guide you through this. Yeah. So first of all, here, this is the standard quantum limit I mentioned before. But actually this is hypothetical. So the real quantum noise, which I get, is this blue line here. Yeah. So you see they use some advanced optic system where they can here slightly overcome the quantum noise, but they have to pay a price. In other frequencies, they become less sensitive. Yeah. Then there's a mirror thermal noise. I didn't talk about this. It's also mostly not important. So let's just ignore this for the moment. And then we have here the vertical suspension noise. And you see here clearly 3 resonances. The 3 resonances are actually, as I said before, we have 3 coupled harmonic oscillators. They have 3 different eigenfrequencies. And this is what we see here. Yeah, the 3 eigenfrequencies from the 3 harmonic oscillators. For horizontal thermal noise, this is more complicated. So you see, you don't see on 3 lines here, you see actually many lines. And this is because they can also see what they call violin modes. So they hang on some fibers, some thin fibers, and the extra modes come from some excitations of the fibers. Yeah, so they start to swing like a violin string. Yeah, that's why there are additional modes here. Yeah, which they should also appear for vertical stuff, but they are highly suppressed. Yeah, so you don't see them here in this picture. This is all KAGRA, so we didn't add anything to this. This is not really our work, but we needed this to understand what's going on because we want to compare our dark matter signal to the total noise, which is this black line. Yeah, so you see this black line will appear in the later figures. So what about the dark matter signal? Actually, it's very easy because we understood how this works in the toy model setup. So X tilde is now our vector of the 3 masses, the intermediate mass, the test mass, and the blade springs. Then we have here this matrix. We can take the Fourier transform and put it on the other side. And then we can study the X tilde for all the 3 components, yeah? And look what is the dark matter signal. And then we get some fun pictures. So here's the first one. If we really have a dark matter hit, oh, this is the blade springs. I should have saw this differently. But anyway, so this is when you hit the blade springs, yeah? So this is if we would have a hit just in vertical direction. So we assume the QR is just in vertical direction, not in horizontal direction. Then you see here, again, the 3 eigenfrequencies, but you also see here this dip. And this dip is coming because there can also be cancellation. Yeah, so that means if you do the Fourier transform, these two components have a different sign and they can cancel exactly at this point. Yeah, so to quite some degree. For horizontal direction, the same picture, you see again all these eigenmodes, but then the cancellation picture gets also much more complicated. Yeah, you see also additional cancellations here. Yeah? So in principle, we believe that if you construct an experiment which tries to look for dark matter using technology, this can help you to distinguish a dark matter signal from thermal noise, because thermal noise didn't have these cancellations. Yeah? There might be a way to distinguish the two in a dedicated experiment. Yeah, this is if you have hit an immediate mass. You see actually also the cancellations depend on where you hit your detector. I should skip one figure. What a pity. No, here I have it, sorry. This is if we hit really the test mass, the mirror itself, the mirror which testing for this displacement. And here you see, yeah. But anyway, in all three cases, you see that the signal is way below the noise, but this is actually what we expect already from our toy setup. Yeah, this was very bleak hope to see this. But again, you can do the exercise and say, if you again would make an experiment with very small masses, with very small mirrors, very cold mirrors, that might work. Yeah, I cannot prove that it works, but I believe it's possible in principle. I mean, of course, there must be some further R&D. Then we also did look at space-based experiments. It was a fair question because space-based experiments are more sensitive, but this is a bit simple because they're actually not so much more sensitive, but they are sensitive in different frequency range. So this is quite interesting for gravitational wave people, but for us, it doesn't help so much. So if you look at the, basically the target sensitivity of LISA, this would be this number. So this is they use slightly different units than LIGO. So the noise level should be below this number. Yeah, it's order 1 number, Fermi per second squared, square root hertz, and then there's some scaling. Yeah, so frequency dependent scaling. So our expected strain amplitude, if you make this estimate as before, if you use 1 GeV with 220 kilometers per second, then we find that this is actually 10 to minus 7 Fermi per second squared. So this is much smaller than this one. So also LISA, we do not believe can see light dark matter in the experiment. Yeah, it's just too heavy. Actually, they still have 2 kilogram mirrors, and yeah, as I said, actually they're not so much more sensitive. It's just they're more sensitive in different frequency band, and frequency band doesn't matter for us. We excite all frequencies, so we don't care about frequencies for us so much. How much time do I have left? Oh, I'm a bit late. Let me just quickly say something about this. So many people actually discuss all dark matter in terms of this kind of experiments. This is an incomplete overview. Let me just say, if you look for this, most papers on dark matter and gravitational wave detectors, this kind of stuff, they actually talk about some other kind of dark matter, very light dark matter, wave-like dark matter. Yeah. So if you go to this limit where you go to ultralight dark matter, I mean, eVolt and below masses. Yeah. Then you get a large occupation number, so many particles in the volume that actually you cannot talk about particles anymore. So your dark matter becomes a classical field, and it becomes an oscillating classical field. Yeah, there's some Lagrangian about this. There's some string moduli inspired stuff. So the point is then that your dark matter becomes waves, and your typical wave looks like this. Yeah, so you get a sign which depends on omega. This frequency depends on the dark matter mass. There's some spreading. Actually, the group velocity is then the dark matter velocity, what we call dark matter velocity. So you get this kind of stuff, and you can all try to make some constraint. People worked on this, and this is what you could get. And you see here the dark matter masses are, actually 10 to minus 12 eVolt. Yeah. So this is a very different thing. And in this case, you really look for a wave going through your detector with your frequency. That means you look in your Fourier spectrum of your signal, you look for a frequency peak at this frequency of the dark matter, which we don't. So there's a big difference. So yeah, I wanted to say just brief something about wave dark matter. So let me come to some of my conclusions. So gravitational wave astronomy has just begun, and I think that's very exciting. Yeah, but I'm not working on this, so maybe I should, but maybe I'm too late for this. The good thing about this is I think they're very impressive new technologies, and I think we should try to ask ourselves, what can we do with this technology, which the gravitational wave people didn't think about, because there's just some physics they have not, they don't work with every day. Yeah, so this is what I want to talk about, this kind of stuff. So can we find dark matter with this kind of technology? And well, I tried to look, first of all, try to find cosmic linear background, and the answer is unfortunately no, this is not going to work, probably not with the setup. There are other proposals which might work, but I'm not talking about this now. Dark matter, I must say, maybe. Dark matter might work, but it strongly depends on the properties of dark matter. So with ultralight dark matter, they can already provide some constraints. With light dark matter, the experiments which are currently there are not working, but maybe with this technology, we could construct an experiment which can be competitive or even better than conventional experiments. And yeah, we might also explore other regions. Yeah, so definitely, I think dark matter at gravitational wave detectors is a very young field. There are not so many papers, and they're very scattered. So it's not, to me, at least to me, it's not clear yet what we can really do about this and what not. Yeah, but I'm working about this to find out what we can do about this and what not. So I think there's still, maybe we can do something about this. Yeah, it's good to do something which is new. Yeah. So yeah, that's it from my side. Thanks a lot for your attention, and yeah, if you want, of course, you can ask more questions. Yeah.
Thank you very much, Martin, for a very nice talk and interesting ideas. So we have time for some questions. Who would like to go first?
I can maybe go first. Can you go back to the slide where you showed the sensitivity in terms of the dark matter cross section?
Do you mean this one?
Yeah. Yeah, I was kind of struggling a little bit to understand this plot, because you have a red curve, which is experiment with noise and curve, and then an idealized curve. The realistic curve be better than the idealized curve for a certain, for the higher dark matter masses.
Yeah.
And everyone's agree to my interpretation of the word idealized, I suppose.
Yes, that's a good question. We have it in our paper. Let me check if I have it in backup slides. I'm not sure if I have it in my backup slides. Otherwise, I can still try to explain you. So yeah, why is this the case? So this is the point. So if you do this, if you look at the distribution, it's asymmetric. Yeah. And if you start to cut at the distribution in the center, with the recurve, if you just say you cut off a minimum recurve momentum, your asymmetry becomes larger first. Yeah, you can see this here. So this is the cut on the recurve momentum. Yeah, we just start to increase it here over the horizontal axis. And this is the A you would expect. So if there's no cutoff, you get something like 0.4, but then it starts to increase and it goes up to 1. 1 is actually the point when you start to cut off all the recurve momenta which are, let's say, negative, because it's asymmetric, so the maximum recurve momentum is different on both sides. On one side is larger, and at one point you cut off all the one side, and you're only left with events which are in one direction, and then your asymmetry becomes larger. And if this is all observable, it means that increasing the cutoff can increase A. That means we become more sensitive. Yeah. Because this is how it works. This is that was a bit surprising to us as well.
Does the number of events go down then?
Yeah, the number of events go down, but still, there's a region where you can win.
Mm-hmm. And you didn't mention anything about Earth scattering. So your cross sections that you were showing were quite large, and there's when you have those large cross sections, typically you have to take into account the fact that the dark matter is going to be stopped by the Earth, and it can also be stopped by the overburden if your experiment is deep underground. I mean, I don't know how deep these experiments are, but at the very least, it would be giving you an additional source of daily modulation. And if it was out of phase, then it could be disrupting your value of A. But maybe the cross sections are not right. I mean, did you take this into account?
No. just plain no. But also, to be fair, the point is in this paper we've been very agnostic because there's no experiment which does this. So this question of overburden, we just don't know. If you don't know where it is, how do you want to simulate overburden? Yeah. Of course, I mean, LIGO's actually, you saw this picture, LIGO's on ground, basically. It's like 2 meters underground or so. KAGRA will be under a mountain, so KAGRA is actually hidden. But then, yeah, I mean, it's the optical limited experiment. I think this was just in a lab in Yale, so there's basically no overburden. So it's a fair point, but I think this is a question you have to answer once you really try to construct an experiment. And right now, I could always cook something up, which I like or don't like.
Are there more questions? Maybe I can ask one. So there is basically, so for your dark matter or neutrino detection, you need much lighter masses. So how realistic are those estimates for the sensitivity, or how? Because LIGO has much heavier mass, or KAGRA as well.
Well, this is a good question. That's why I showed this. Yeah, actually, this is a typical. Yeah, if I would only know. Let me just put it like this. So the reason why I believe it's not utopic is this experiment. Mm-hmm. So they have a target mass of 1 nanogram, which is super light. Yeah? Yeah. Of course, there's one drawback because the lighter target masses you have, the less events you get because there's less chance for dark matter to interact with your target. But of course, you get more sensitive in a sense. The big question is basically like all these noise levels, which KAGRA and LIGO have worked out very detailed. How does this translate to this kind of experiments? And what is the ultimate limitation in terms of physical background, which you can not avoid? Mm-hmm. And to be honest, I don't know. I mean, quantum limit, you can say you can scale, and then you would be in trouble if you make things lighter because it goes with 1 over mass, but it goes also with 1 over omega squared. That means if I go to much larger frequencies, I can again start to suppress the quantum noise. Yeah. But then you can ask, so what kind of frequencies can you get? Is there some new noise, new kind of source of noise at very large frequencies? It's a good question. I simply don't know, to be honest. Yeah, I'm optimistic, but I'm also a serious guy. Most experimentalists I met, they've been very negative, especially gravitational wave people seems to be very negative about this. But I think they are sometimes too harsh and too narrow-minded. Yeah. Because that's the point. I don't want to rebuild LIGO with a 1 nanogram mirror. Obviously, that doesn't work. Yeah, but it doesn't mean that we cannot make an experiment which has a 1 nanogram target mass, because obviously it exists. Yeah. The question is then just can we combine this technology with an optics which is as good as the optics LIGO has? And then I must simply say I don't know.
Yeah. Fair enough. Fair enough. That's the initial idea. I would say we thank Martin again now because it's already 5 o'clock, but he has more time to answer more questions. So thank you very much, Martin, for a very nice talk. And so if you have to leave, you can leave, but if you have more questions and so on, Martin is happy to answer more questions.